Cool. So in the last class we started to look at the folded cascode, and that was basically the same cascode you guys are familiar with, just presented in a different way. And just to jog your memory, cascode basically had a common source stage like this, which takes in some input and generates a current acting like a voltage controlled current source, or you can have a proper current source like this. And what we did was we added a current buffer here, which was realized using a common gate configuration, right? So I'll just show one here. And the common gate in turn can be realized using either an NMOS or a pMOS. So when we had the same kind of transistors for both the bottom current source and the cascode, we had the normal cascode, and when we had different flavors, that basically gave us the folded cascode. So it's basically the same old, like just like how we have in Indian movies, same stories, same thing, no difference. So let me quickly draw the circuit with NMOS input. So we had the NMOS stage, the single-ended, and this current was buffered to a pMOS current buffer, and at the bottom we had another current source which we realized using an NMOS cascode like this, and to bias it you have a current source here. And in the differential picture we had let me maybe push it slightly here. So in the differential equivalent we had this guy, but we connected this to a tail current source, and then we made a copy like this. That's all. Right? So let me label it quickly. And so this gave the same gain as the telescopic cascode, but what was the advantage here? The swing was higher. I mean, in particular, when you put it in a unity feedback like this, the swings you got was actually much higher, right, compared to a telescopic cascode. And also the second point we noted was, if you just look at the maximum input common mode that you can apply, what was that? Yeah, that could actually reach, it can in principle be higher than VDD, so the input can be at VDD. Okay. So by the same logic, we postulated that if we were to have a pMOS input stage, then the input can be close to what? The input could ideally be close to 0, right? And this is what we started to look. And one of you guys, he's not come, I forgot his name, he was brave enough to come and try it on the board, and with some of your help we kind of made it. But then I asked you guys also to work out. Did you guys try it? Huh? Okay, now someone wants to try it on the board. No, not on the air, no, on the board. I can show the NMOS cascode. I mean, first someone can draw the single-ended version. It's okay. Sorry? Yeah. You explain what you're doing also, right? So that everyone knows. So yeah, as Pushpender helped last time, I received. And yeah, so he has also drawn it now. So what's your name? Shubham. So I mean, the idea is same, right? We wanted to have first a common source followed by a common gate, right? A common source pMOS will look like this. Oops. With a pMOS, common source will have to apply input at the gate, right? Source is basically incremental short. And then we need to have an NMOS current buffer this is the NMOS common gate where the current is given to the source and we'll take it from the drain. And at the top I have ideally should have a current source like this, which we'll realize using a pMOS cascode. And at the bottom you have a current source for biasing. That's all. That's fine. Now if you want to draw the differential picture, I mean again incrementally the source is short, but you try to connect it to VDD in the single-ended equivalent. Now in the differential thing, the same, we have a copy of this guy. I'll just flip it and draw for symmetry. Like this. So again, you can do this also, but instead we'll connect it to a current source here. Okay. And by the way, so that reminds me, so if you want to have a differential amplifier, you can also do this, right? I can take V1, V2 and put loads here and take the output. But instead we are doing this. We put a tail current source here. So why are we doing this? I mean, I can do this also, right? I can apply I can take two separate amplifiers like this, apply one input to one of them, second input to the second, and take the difference. So this seems to be simpler, right? Why am I adding this extra current source here now? Is the question clear? I mean, so everyone is familiar that a diff amp we have been using is this. Two common source stages with their source connected and bias current here, right? And we have some load here. I mean, let's not worry about that for now. What I'm asking is, why don't we do this? Just take a common source, take a copy of it. Say here I apply plus delta V and minus delta V. So here I apply plus delta V by 2 and minus delta V by 2 and connect the loads here. Huh?
The delta V.
Sorry?
V1 and V2.
Yeah, that's okay, fine. V1, V2, whatever, right? That's fine. Sorry? Noise. I mean, let's not worry about noise. Is there something even fundamental? I mean, this will work, right? So, what is it? Yeah, see, we want the op amp, like you mentioned, to respond only to V1 minus V2. If both V1 and V2 increase together, we don't want the op amp to respond, right? So in this case, the second one, it doesn't matter if V1 and V2 are increasing together or in a differential way, it is going to respond. But what can you say about the circuit in the left? Again, we are trying to look at the common mode response. So you try to draw the common mode equivalent. What is it? So at common mode, both of them are at the same input, delta V, delta V. So which means I can say these two nodes are at the same potential. I'll short them. I should keep forgetting to do this. So you get basically this, right? So now, irrespective of what delta V is, I am forcing the current here to be some I naught. So which means this voltage, will it change or not change? Huh? It will be fixed, right? So even if I change this gate voltage, the output is not going to change, right? I mean, that is why we do this, right? Okay, is it clear? Okay, so let me just get back to this one. Yeah, so this is the folded cascode. Again, to get a single-ended version, I'll have to do a diode connection. And where do I do that? Okay, I forgot M1, M2. Say this is M7, M8. M5, M6. So where do I do the diode connection? Gate of M7 to, that fine? Okay, great. So now let's try to calculate what is the minimum common mode input you can apply here. So what is the minimum input? Basically, if I keep reducing the gates here, which of the transistors will have issues? The main diff pair, right? So what is the minimum the gate can drop to? If I call the drain voltage here as VD2 and VD1, minimum of input is whatever drain voltage can be minimum minus a threshold voltage, right? 1, 2, whatever. Sorry, minimum it will be minus always. Okay, is that okay? I mean, it's a pMOS. If you keep reducing the gate too much, the transistor will go into triode. And again, now this will also be realized using a transistor. And what kind of transistor might this be? The current source here? pMOS or NMOS? NMOS, okay. I mean, the idea is for a current source, gate and source voltages must be fixed. I mean, if you have to put, here you see gate is fixed to some bias, source is fixed to ground. But if you have to use a pMOS, you will have something like this, where the gate is also not fixed. I mean, source is not fixed. This will not act like a current source. Okay. Yeah. So now, what is the minimum drain voltage? If I call this M10, M9 and M10, what is VD2 minimum? It's overdrive of that particular transistor. So that is overdrive of 10 at a current, say I1 minus mod VTH2. Okay, and this is obviously, oops, it's a disappearing pin. The current I1 minus mod VTH2, and this can obviously be less than 0 in principle, right? Because overdrive can be say 0.1 or 0.05 volt, and threshold will be 0.4, 0.5 easily. Okay, so basically with a pMOS folded cascode, the input can lie at 0. Right, and if you had an NMOS, the input can be at VDD. Okay, and actually this is happening because the common mode range here is much better, because if you look at the telescopic cascode, this was VB4, and if you think about it, both the input and the output was governed by this 1 voltage VB4. Okay, in other words, the input and the output common mode had a strong coupling. They were strongly dependent on VB4. But here with the folded cascode, I don't know where we derived it in the last class. Yeah, in the folded cascode, you see that only one is fixed by VB4, other is actually not. Other is actually fixed by this. So what I am trying to get is that if you have a folded cascode, the input and the output, they are no longer strongly coupled. This transistor kind of decouples it. Okay, so that is that's what happens in a folded cascode. So this is one advantage with folded cascode. So input and output common mode ranges are I will say less coupled, and if you had an NMOS pair, NMOS input, VA can be at VDD, and with the pMOS input, VA can be close to ground. I mean, this is the main reason why you might want to use a folded cascode, right? Because even the telescopic cascode gives you the same gain, right? But here you see in a folded cascode, you have an additional branch. So this guy is the additional branch. This is taking additional power anyways. And the trade-off is that you get a better input and output space. Okay, great. So now for the folded cascode, we have found the DC gain, operating point, common mode range. What is the last thing we'll want to do? Slew rate. So let's do that. Let me see if I can copy this guy. Okay, so let me call this current I0. If the quiescent current in this branch is I1, what is the value of the current sources? I0 by 2 plus I1, right? So again, let's do the slew rate quickly. So for slew rate, again, I'll assume that we are applying a large differential step at the input. Say we have a capacitor here. So now I apply a large differential step with this polarity. What might happen? M2 might enter cutoff. So I'll just erase it from the picture. All the current kind of flows like this. So this current will be I0. So this current will have to come like this. So this is I0. So this current is I0 by 2 plus I1. So what is the current flowing in this branch? That's fine. I1 minus I0 by 2. There's a difference between the two. So what we have here is a current mirror. So this guy will, the transistors to the right will simply follow what current flows in the left branch. So this current is also minus I0 by 2. Okay. And note that here there is no current flowing, right? So the current flowing in this branch is 0. Okay. So and here this current is obviously same, I0 by 2 plus I1. So we have I0 by 2 plus I1 flowing here, I1 minus I0 by 2 flowing here. The current flowing to the capacitor is I0. Okay, so slew rate is again I0 by CL, and again if you take a negative step you will get the same thing. Okay, but let's look at the currents I have marked here, and can you tell me if I have made some assumptions in getting this? I mean, look at all the currents which I have marked in blue and tell me if something bothers you. Some of the current bothers you. Okay, can you elaborate more? See, here I have assumed that the current here is I1 minus I0 by 2, right? So what is the minimum current we can have here? 0 is the minimum, right? So here I have inherently assumed that this is the deal. Okay. So let's quickly see what will happen if you have it the other way around, because this was not a constraint at all when we derived the circuit. You are free to choose anything. So let's quickly see what will happen if you have to choose the other thing. So let me do that. So again, let me explain what might happen is, so for very small delta V, there is going to be no slewing. Okay. And if you have a large delta V equal to a delta V max, this current is going to get steered, ideally, if this condition is satisfied. Okay. And what will this voltage be equal to? Does anyone remember? Root 2 times the overdrive of the differential pair at a current I0 by 2. Okay. This will happen. I mean, this steering will happen if I1 minus I0 by 2 is greater than 0. But if you choose the other way, what will happen is before you can reach this amplitude, Yeah, so even for a smaller amplitude, say somewhere in between, I'll call delta V prime. What will happen is the current flowing in this branch will become 0. Okay, so this current will drop to 0, right? So let me erase all the other currents which I have drawn. So which means this current is no longer 0, right? Because there is no complete current steering in this branch happening. Only thing we know is the current here is 0, right? Oops, yeah. So yeah, I'm sorry, this is connected now. So if the current here is 0, I know that this transistor is cut off. Let me just remove this guy for now. Okay. So if you choose I1 to be less than I0 by 2, so M3, M5, M7 will be cut off. Okay, that is for a smaller amplitude delta V, which I call delta V prime. The branches here M3, M5, M7 will cut off. So again, this is a current mirror. So what will happen if this branch is cut off? This guy is also off. Okay, so this is also off. Current here is also 0. Fine. So if the current here is, I mean, now you see that there is no connection here, it's an open circuit for now. So the current flowing from the current source is I0 by 2 plus I1, that has to flow here. Fine. So this current is now equal to I0 by 2 plus I1. Okay. So if this is I0 by 2 plus I1, what is this current? I0 by 2 minus I1, because this current is fixed at I0. Fine. So this current basically comes like this. So this is no longer 0. This current is I0 by 2 minus I1. Okay, so now you see that this current source is pumping in I0 by 2 plus I1. The branch here is taking I0 by 2 minus I1. The remaining current is what will flow into the capacitor. And what is that? 2I1. Okay. So if you choose the other case, what is the slew rate you can have maximum? 2I1 by CL. So the slew rate is okay.
So this is the case when the delta V will be
Correct.
in between 0 to delta V max.
Yeah, correct. I mean, basically, at some point, see the differential pair, the current here will in one, ideally the currents in M1, M2 are this with 0 delta V, right? If there is a differential step, this is going to take some delta I, this will have minus delta I. At some delta V prime, this delta I will become equal to I1, and this will happen. Okay. Before you can even have complete current steering in the differential pair, this will happen. Is that fine? So now, I mean, that begs the question, so what if I apply a much larger step? Say I apply an amplitude greater than delta V prime. What will happen? Yeah, but I mean, the current is still same, we can't give anything more, but the diff amp will demand more current, right? Now what I'm saying is delta I can be greater than I1, that's the demand you are putting in because you're applying a larger step. Sorry, this is a mess. So what I'm saying is, let us say if delta V is such that the differential current in the M1 M2 is greater than I1. So what will happen?
It cannot follow the input slope.
I mean that this is the slope, but what I'm asking is, so here the current that will be demanding is greater than I0 by 2 plus I1, right? But we just have a fixed current source of I0 by 2 plus I1. So we can only pump in so much current, right? But the transistor is saying I want more and more current. So what will happen? Sorry?
To not get the
Transistor can go into other.
So can you explain more?
If it requires more current, it can go to triode.
No, if you go to triode, how will it have more current? If you remember the characteristic of MOSFET. But I mean, if you has a slight point, see, this current is fixed, right? So let us say I call it some I prime, or just say IA. Now what I am saying is the transistor is trying to pull a current that is greater than IA. So we are pulling out more current from this node than we are pushing in. So what will happen to that node voltage? It will decrease. Okay. So if I call it VD1, then what will happen is VD1 will drop. So VD1 will drop. Then what will happen to the transistor? It will enter triode, and that way the current will drop and finally be equal to this guy. I mean, because that is the maximum current you can have here, right? So the drain voltage will drop automatically to make sure that the current is equal to this. Okay, so this will imply that M1 enters triode. Okay. So now that's a choice for you, right? So what would you do? Would you choose I1 to be smaller than I0 by 2, or I1 to be larger than I0 by 2? If you are going to design a folded cascode, what would you choose? Why? No, if you choose I1 smaller than I0 by 2, it might happen. I mean, at least it makes sense, right? Slewing is something you want or you don't want. You don't want. You want the op amp to provide as much current it can provide, right? And here you see that for a smaller amplitude itself, this slewing happens. But if you choose the other one, you can have a much larger amplitude. And not just that, in this case, you see transistors can enter triode region. So it will take more time for the op amp to recover and enter into saturation later. So a better choice is to choose I1 greater than I0 by 2. Okay, great. So now let's quickly see what we have been looking at. So all this time we have been trying to increase the gain of the op amp, right? And if you recollect, the GM we had was GM1 of some transistor. The only thing happening all this time is we have been increasing R out. And in the first case, when we had the 5 transistor OTA, we just had one transistor which had an output resistance of R0. So ideally, if this were a current source, we had no issues. But this is not an ideal current source. It had an output resistance. So then we put a current buffer and got a cascode. So here, what was the output impedance? So it was basically some GM R0 square. So this gave us a gain of GM R0. This will give you a gain of the order of R0 square. So now let us say I want a gain of the order of GM R0 cube. What will you do? Huh? Sorry? I actually keep another cascode. That's what you're saying, right? So you can put one more cascode here. So this is the normal cascode. can obviously put one more cascode or have a telescopic cascode or whatever you want. But the point is you have to stack 3 devices like this. But if you do that, what will happen to the swings? What will happen to the output swing? What is the minimum the output can go now? It is going to be 3 overdrive voltages. Here it was just 2 overdrive, and here it was just 1 overdrive. And as you keep stacking more and more devices, you are going to lose out the maximum output swing, because each of these transistors will need a minimum drain to source voltage. So that is the price you will have to pay. So you gain something, obviously you will have to lose something. It's a trade-off. I mean, nothing is free in life, right? Okay. So, but let's look at let's look at the same thing in a different angle. So now we had a current source which had an output resistance R0. What we told was we wanted to increase the output resistance of this guy. So the idea was to have a current buffer like this, and this gave us the cascode. So here if the output, this voltage changes by delta V, can you tell the change in the current delta I? It's incrementally short, right? If the drain voltage here changes by delta V, delta V by R0, is that fine? So here if I change the voltage by delta V, what will be delta I? Same output resistance, right? So if I call this delta V2, what is delta I in terms of delta V2? Is that fine? I mean, because if you have the incremental equivalent, you just have R0 of this guy, you have delta V2, and then you have the rest of it here, right? So this is delta I, the same current delta I flows here. Okay. So this is basically delta V by GMR0, and that's basically what we saw in one of the classes also, right? If you change this voltage by delta V, the change here is very small, and because the change here is very small, the current change is small, and you have a higher output resistance. Okay, so the point to note is, if you can have zero change in delta V2 irrespective of change in delta V, that is, if delta V2 is 0, what can you say about the output resistance? It will be infinity, right? Because if delta V2 is 0, this will automatically mean delta I is 0, right? So what does this mean? Incrementally delta V2 must be 0. So which means if I call this voltage as VD2, VD2 must be constant. If by some means, if we can ensure VD2 to be constant, irrespective of whatever happens somewhere else, we can guarantee an infinite output resistance. Is that logic correct? Okay, so now let me take this thing again. So this is the cascode. You're okay with this point? If delta V2 is 0, you have infinite R out. Yeah, incrementally delta V2 is 0, but finally it should be at some constant bias voltage, right? This is the total voltage here. I mean, absolutely it cannot be 0, right? It cannot be equal to 0 volt. Yeah, that's all. There should be some bias, but no incremental change. Okay, so now this is the deal we have, and we want to fix this guy. So let me label it as M2, M4 again. We want to fix VD2. So in this circuit, what actually fixes this drain voltage VD2? the gate voltage of M4, right? So VD2 is fixed by VB4 minus VGS4 at some current I, let's say. Okay. So now let us say you are in a lab setup and you want to do this. Let us say you want to have, let me push it here. You want to keep VD2 equal to some reference voltage Vref. So what will you do? I mean, you are in a lab, you are given access to all the terminals in the circuit, and you also have a reference voltage Vref. Your goal is to fix VD2 to be equal to Vref. I mean, in words, what will you do? No, I mean, this is plain English, right? I mean, this is as simple as, you want to have, heater, your water to be at some particular temperature. You can sense by putting your hand in the water and see what temperature is, and you can control the knob for the heater. What will you do? Huh? Yeah, so in English, what will you do? You will actually sense what is the temperature. If it is higher, you will reduce it. If it is lower, you will increase it. So here, what will you compare? We will have to sense the difference between these two guys. Okay, so you will basically sit in the lab, you look at this guy, and then based on this, you will go and correct it. So, right, I mean, first formulate the solution in English, and then you can, if you can formulate in words, you can make a circuit for it. That's all. So, of course, you can't go for each and every circuit and keep doing it. That's not a possible solution. I can't ship a human being. So, we'll have to have some arrangement here. Right? So, that basically will take Vref. Something should come and control this voltage. Fine? And if I call this VB4, VD2, ideally VD2 is equal to Vref. That's what you want. And obviously, VB4 is some finite voltage. Right? So let me probably slightly. Okay. So if I call this error voltage VE, what is VE then? Yeah, but ideally VD 0. Okay. So now you see you have a block which takes an input which is VE, which is 0, and an output which is VB4, which is finite. Right? I mean, you have a block which has a 0 input and a finite output. So what is the gain of the block? Infinite. So what block provides an infinite gain? An ideal op amp. Right? So basically here, if you replace this guy, let me draw it again. With an ideal op amp like this hopefully should work. Okay, so this is going to be my Vref. Okay. Oops. Sorry. So now, I mean, we need to find if the signs of the op amp we have put is right. So let's quickly check. So if let us say the drain voltage increases for some reason, this increases. So what will happen to the this voltage? It will decrease, right? So if the gate voltage decreases, what will happen to this voltage now? That will decrease. So it's in the correct sense. It's a negative feedback. Okay. So this is the idea we have. So what we have is this, the old cascode. But if we have an ideal op amp, then the output resistance goes to infinity. Okay, so we'll stop here and we'll continue in the next class. So the last